Welcome back to Advent of Code 2018. We're on to day 10. Looks like we've got some sort of physics problem. All right. The stars align. It's no use. Your navigation system simply isn't capable of providing walking directions in the Arctic Circle, and certainly not in 1018. The elves suggest an alternative. In times like these, North Pole rescue operations will arrange points of light in the sky to guide missing elves back to base. Unfortunately, the message is easy to miss. The points move slowly enough that it takes hours to align them, but have so much momentum that they only stay aligned for a second. If you blink at the wrong time, it might be hours before another message appears. You can see these points of light floating in the distance and record their position in the sky and their velocity. The relative change in position per second. Okay, so that's basically their velocity. The coordinates are all given from your perspective. Given enough time, these positions and velocities will move the points in a cohesive message. Rather than wait, you decide to fast forward the process and calculate what the points will eventually spell. Oh, so are we going to have to actually interpret this visually? Alright, so we got a bunch of lights, they have a position, and they have a velocity. Okay. Each line represents 1 point. Positions are given as XY pairs. Yeah, usual stuff. Blah, blah, blah. Okay. Ha! Will take many more seconds to appear. What message will eventually appear in the sky? Oh god. It would be... I don't have any visualization libraries installed. Or nor do I really know from the top of my head how to use them. But animation libraries certainly have been used by people in Advent of Code. It's quite useful in some cases. This is one rare case where it would be extremely useful. Well, hopefully we're not talking about thousands of seconds, so otherwise how would you do it? Maybe try to find a frame where they're all lined up in a line. Like, say we notice that these 8 are in a line, and that will kind of give us a clue that that's the message. And then just print that one. Yeah, maybe. Okay. We could... Alright. Got to find the message. ChatGPT wouldn't be able to solve this one. Well, he probably could, but I mean, he wouldn't be able to see the message himself. Well, maybe he could. Alright, so... I don't like this format. That's a tab? Well, okay, Why did they have to do it like this? Oh, it's fixed width. Oh, that's okay then. I can use that. All right. Okay, let me grab my coffee. Okay. So we need so we want to store the positions. Should call it XS equals that, VS equals that. Line in. All right, so we want so it'll be 10 to 16. Hang on, so it'll be XS.append line 10 to 16. So it'll be int, that needs to be an int. Int line no. Hang on. So that'll be 18 to 24, but it should be yeah. As a tuple. 18 to 24. Okay, so that's the position. And the VS, so the VS will be 36 to 38. And 40 to 42. All right, let's just print these. I want to see what these look like. Minus 976750146. That should be the first one. 1 minus 5. Okay. Alright. Now... should we make a method which let's call it display? That means we basically print a visualization. Let's say with spaces and hashes. So we have to decide on okay, so it's going to be min x equals minimum of minimum of xs. Let's just key equals isn't there like a method which is like no. Okay, key equals lambda take the first element. So we're taking the lowest x value. Take the x out of that. So just do this 4 times. So it's going to be min x max x equals max min y max y min max, so let's key equals lambda p, take the ones. So that knows kind of our range. So basically we want a grid also y value is positive downwards, okay. Okay, so we just want to make a grid of this width with these, a restricted grid, which is fully contained around every point we have. So the closer the points are together, the more zoomed in our grid will be, just for the sake of the display. So we want to make grid equals, let's say, empty space for now for x, y in xs, we're gonna do grid. So the y value will be y minus min y, and the x value will be x minus min x equals hash. And then finally, for row in grid print, just join it up. Let's test this out. So display xs. What? Oh, because it's very big. Alright. Alright. It's too big. Let's say we wait until they're all together, so it's like less than 1,000 or something. So this is gonna take a long time still, because even this min-max calculation is maybe these should be variables we keep track of. No. Because we're running through the XS every time we call display. That's 379. And it'll take thousands. That's not too bad. All right, let's say let's just do this. Max x minus min x n equals x y minus min y. Use these variables. So should we say if n is less than, I don't know, 250 and m is less than 250, how big do we think the message would be? So display right now should not do anything. Okay. So waiting for them to get closer together. Okay. So now we have to do the actual physics process of this. So we need to say while true, if so for I in range length xs, xs I equals xs I 0 plus vs I 0 xs I 1 plus vs I 1. That updates. So we display xs each time, and then move them by 1. Let's go on forever, so as soon as we see something happening, we can maybe stop, I don't know. Y minus... or xy in xs. What? List index out of... So we've got n and m smaller than 250. So we make a grid of 250, at most 250 by 250. For xy and xs, grid y minus min y. Y minus min y can be at most n. How can this be out of range? Hmm? Min... Oh, wait. We need one more, plus 1. If 2 points were next to each other, there'd be 1 apart, but we need 1 more. Yeah, that's right. God. Alright, stop. Well, we printed something. Does anything look remotely like a message here? I think I saw something. squint my eyes a bit. It's too hard to tell. If I wanted to fit on the screen, we should reduce it then, mate. Let's go 100. There we go. CZKPNARN. What is that? CZKPNARN? That was an interesting one. Alright, well, there's absolutely no way that's wrong. It's gotta be right. Good thing you didn't have to wait, because that would have taken a long time. Much longer than the 3 seconds in the example above. Impressed by your sub-hour communication capabilities, the elves are curious. Exactly how many seconds would they have needed to wait for that message to appear? Huh? So we just print the number of seconds, what? We would know, right? Because that's the iteration in which we saw it. I don't see how this could possibly be difficult. We just need to print, alright, let's say for time in count. Print time as well. So we just have to, so the starting one will print 0. Yeah, okay. Damn it. It would help to just print it if we are displaying stuff. Hello, CryptoPie. Aha. CZNARN at time 10,003. Is that it? This is a really easy part too, if that's all we need to do. Okay. Nice easy one there. Easy part 2, I mean. Part 1 was fine, but it required manual observation. Okay, on to part 11. Oh, it's raining heavily. Chronal charge. You watch the elves and their sleigh fade into the distance as they head toward the North Pole. Actually, you're the one fading. The falling sensation returns. The low fuel warning light is illuminated on your wrist-mounted device. Tapping it once causes it to project a hologram of the situation. A 300 by 300 grid of fuel cells and their current power levels. Some negative. You're not sure what negative power means in the context of time travel, but it can't be good. Each fuel cell has a coordinate ranging from 0 to 300 in both the X and Y. Okay. The interface lets you select any 3x3 square of fuel cells. To increase your chances of getting to your destination, you decide to choose the 3x3 square with the largest total power. The power level in a given fuel cell can be found through the following process. Find the fuel cell's rack ID, which is X plus 10. Alright. Begin with the power level of the rack ID. Okay, rack ID times Y. Add the grid serial number, which is 2866. Multiply by rack ID. Modulo 100. Take away 5. Okay, that's a straightforward arithmetic. There's no iterations in it. Okay. And then we just look through and find the grid with the highest power level. What is the XY coordinate of the top left fuel cell of the 3x3 square with the largest total power? Okay, I don't see anything hard here. So we need a 300 by 300 grid. So there's no input here, just 2866 is the grid serial number. Okay, so we've got, let's say, power equals okay. So we might as well just fill that power. So actually we can do this. So we create a method called define get power for a given X given Y. So we go through this process. Let's start from the top. So the ID, let's write this out. Rack ID is X plus 10. Rack ID equals, but their X is 1 more than RX. RX starts from 0. Theirs starts from 1. So we want X plus 1. Just write it out fully so that I remember. Power equals rack ID multiplied by Y plus 1. So power equals rack ID times Y plus 1. These numbers can be negative as well. Add the serial number. Multiply by rack ID. Modulo 100. Oh! No, not modulo 100. We do, we keep the hundreds digit. So we want to divide by 100 and then take the last digit that's remaining. And then subtract 5. So you can immediately say that we get power x, y for x in range 100, for y in range 100. Okay, let's run that. Okay. Now we need to find the largest total power. Okay, so let's say best, and we want to give the top left the xy coordinates. Okay, so best xy equals none, best power equals none. Alright, so then we do for x in range 300. Or let's do 298. For y in range. Let's be clear on what we're doing here though. So it's 300. But it's going to be minus 2. 300 minus 2. Just so I know why I did that calculation. So that will mean we always get a 3x3 grid. So we say power. Oh, let's call this power grid. All right, so power equals 0 for dx in range 3, for dy in range 3, power plus equal, so we're going to do power grid, so the y value will be y plus dy, x plus dx. So then if we've found a better power, best xy equals xy, best power equals power, print best xy, but we're gonna have to add 1 to those. Oh. Whatever, just do minus a million. Is there an inf in Python? 1949, so 2050. What is the xy coordinate? How do they want this entered? Oh, I guess we just put a comma between them. 2050. You discover a dial on the side of the device. It seems to let you select a square of any size, not just 3 by 3. Size from 1 by 1 to 300 by 300 are supported. You must find the square of any size with the largest total power. Oh no. This is going to need something efficient, isn't it? Because it's going to be... Oh, it's 300 by... 300 by 300 by 300 by 300 in the worst case. What's that? 300 to the power of 4. $8 billion, but it's not going to be that much. It's going to be less than that because a lot of the rectangles are smaller. So could we actually do it? We could try. But yeah, we're going to have to do something efficient here. Ugh. I just hate having to be efficient. Yeah, I've done problems like this before. What's the best way usually? You want you want to keep a table of basically, you want to know every rectangle which starts from the top left of the whole grid. You want to know every such rectangle, and then if you ever want to find a smaller a square or a rectangle somewhere in the grid, you can just take the whole rectangle from to the top minus the inner rectangles. There's a way of doing this. Should we just try the slow way though? See if it works. So it'd be this again, but so be X, Y. So delta equals okay. For delta in range, let's say 300. So it will go X to 300 minus delta plus 1. So, for example, if we wanted to have the whole of the grid of 300, it'll be for X in range 1, i.e. just the starting point. That makes sense. Delta plus 1. Power equals 0 for dx in range. So it's going to be delta dy and delta. This cat stays the same. Alright, this is going to take too long. Let's just try it. Just see how many deltas we're getting through. So we're waiting for that to get to 300. But yeah, look, it's slowing down a lot. Actually... Alright, let's just leave it running, see what kind of momentum it gets. It's slowing down, but it's still doable. See, we're in the 20 now. Oh, no, we're not going to 30. We're going to 300. Oh, fuck. Yeah, no, that's going to take too long. Okay. So. We need something better than this. So I think we want to keep... Alright, stop this. So that's no good. We need to keep a table of sums of powers for every 2x2 rectangle starting from the top left. So let's try this. Let's take all this out. All right. Table equals. All right. So we want 4 dx in range, let's say 300. 4 dy in range 300. We want to know what the rectangle starting at 0, 0 and going to dx dy. We want to know what the sum of that is. So we want to say table. Hang on. So power equals 0. So it's going to be basically this. We'll say this. For, let's say, x in range, y in range. So dx, dy. Power plus equal. No, but it's just going to be y and x. So that's the width. X in range dx. And then table dx dy equals power. So we've stored the power for that rectangle. How long does that take to run? Don't tell me that takes too long too. It's 300 by 300 by... Oh no, that's still going to take too long. Okay, we can break this down further by using recursion. Wait, hang on. Fine. How do we get this size of this rectangle? We basically have to take the smaller rectangle plus... Okay, so if all right, there's two cases. If Also, we kind of want to go 301. So width 1 is the first one. It's just a basic rectangle. Okay, let's say if dy is just 1, that means for a certain x value, we're just taking the top row. So power equals, it would be table hang on. If dx is 1 and dy is 1, this is the absolute base case, then power equals table we don't need to start from 1, just do 300 like before. Alright, so power is table um 0, 0. Hang on, what am I doing? Power equals power grid 0, 0. Okay. Else, if, let's say if dy is 0, then power will be table dx minus 1 dy plus power grid dx dy dx. In fact, let's always use dy dx. Dy dx. So if dy is 0, then we just take the shorter row and then add that one element extra. And then finally, else it's gonna be otherwise it's gonna be table. Okay, so we've got basically 3 things to sum up. We've got table so it'll be dx minus 1 dy plus table dx dy minus 1. Now those 2 rectangles overlap by exactly this amount. Dx minus 1 dy minus 1. So that will give us, so you add two it's hard to do this without a diagram. You add those two overlapping rectangles, subtract the intersection. And then you have to add one more thing. That's just this one new element. Power grid dy dx. And then we say table dx dy equals power. Let's see if that runs then. Key error 1 minus 1 1. We shouldn't ever go to minus 1. Ah, because if x is 0, what do we do if x is 0? That means it's just the leftmost column, so it'll be similar to this. Power equals table d dx dy minus 1. Try that now. Alright, so we should now have a table of all sums which start at the top left. Why are we getting floating numbers? Because we didn't use an integer division. Whoops, that's quite bad actually. But it was close enough that it was... okay, there we go, that's more like it. So we're saying, for example, the full sum of the whole grid is that. Got a lot of negatives. Alright, so we now know every rectangle that originates in the top left. Now, we just have to try every... Okay, so... This would have been best as a method. Alright. Let's define a method then. Define get sum from x1, y1, x2, y2. Starting at that coordinate, finishing at that coordinate. let's say if x2 is less than 0 or y2 is less than 0, return 0, because that might come up in a recursive call. Otherwise, it's this. We do return table of x2, y2. So that's what the table was designed to do. It's the sum of the rectangle up to and finishing on that point. But we need to subtract table, so it's going to be x2, hang on, x2 y1 minus 1, so before the y1, also subtract x1 minus 1 y2, and then we need to compensate by adding back in table x1 minus 1 y1 minus 1. So subtract the left part, the upper part, and then put back in the smallest part because we've subtracted that twice. What you should end up with is just this new rectangle. Oh god. Yeah, I think that's fine. In fact, we could have worked all this into that method, but that's fine. What now? Now we just want to try... Wait, so we now know how to quickly find the sum of any rectangle. But if we range over every rectangle, it would still be 300 to the power of 4, won't it? Which is still a lot. Because now, if I do this, for x1 in range 300, but it'll be reduced, but what we were doing before was this, but we were then doing the sum, which itself takes lots of time. Alright, I don't know, let's try it. For y1 in range 300, so that's all the possible top left points. For x2 in range starting from x1 plus 1 to 300. For y2 in range Starting from y1 plus 1 to 300. Let's just see how long this takes to execute. Get some. Key error 1 minus 1. Oops, I was supposed to use get some here. Okay, so wait, what's going on here? Alright, if x1 is 0 and y1 is 0, then we return table x2, y2. That's what that was for. Otherwise, it's gonna be get some zero, zero, x2, y2. So it'd be like this. 0, 0, x2, y1 minus 1. 0, 0, 1. 0, 0. Let's try that. Oops, don't debug. Stop, stop, stop. Still taking a long time, but it should be faster than the original brute force, but it's still, you still have to try all. Oh, this is a classic algorithm. I think I've done it a bit in a bit of a long-winded way, but it's not quite. Alright, let's see how it's increasing. Say just print x1. Oh my god, that's too slow. I thought the only advantage of this is that we can now compute any rectangle quickly, but we're not. That's just... Oh, I don't remember this. This is a very classic interview problem. What do you do now? Right, it's not wasted effort. We now know how to compute any rectangle quickly. Oh, it's like sliding window or something. Oh man. some sort of sliding window algorithm. Well, not quite. Given... I mean, we could just run this. At this point, we've filled this table. We can skip all the ones we already have, so we can say... well, we don't need to. No, it's too slow. Let me leave it running while I think, at least. Hello, Tesla Fane. Teach me the ways of code. I think you've caught me just as I hit a bit of a roadblock. Intuitively, this problem is easy to describe, though. Basically, we have a... It's better if I print this power grid out first. Oops. Let's see. For row in power grid, print row. So we have this grid, 2x2 grid, 300 by 300, and every item in this grid has a number. Negative, positive. We're basically just trying to find any rectangle. Well, we were trying to find a rectangle of items in here, which has the maximum sum. The sum being the sum of all numbers in that rectangle. So it could be a small rectangle, like 3x3. It could be a huge rectangle, like 100 by 100 in any location. We're just trying to find the biggest rectangle amongst all possible rectangles. And there's about 8 billion possible rectangles. That's the roadblock I've hit. It's too many to try if you just want to try all of them. So I'm trying to think of some clever optimization here. Because I do have... Oh, hang on. Let me get paint out. Oh, you know things are getting serious once I need to whip out paint. Alright, while I'm doing paint, I'll just have this run. What did they want us to compute? They wanted us to compute the XY value and the size. Oh, it's a square, not a rectangle. Okay, that helps. So it has to be a square. That cuts down a whole factor of like 300. Because then we're ruling out all the rectangles. Alright, well, before I rerun this, let me refresh my understanding. Alright. That is supposed to be paint. Oh, because I've done a chroma key, because I was doing something... Ah, wait, so if I were to change the color to... How did I set this paint thing up? Ah, there we go. I did have some sort of chroma key. Anyway, it doesn't matter. I'll sort that out another time. So... Really want to learn basic Lua to build a cheat engine trainer with drop-down menus, etc. Yeah, it would help with cheat engine. I've looked into cheat engine once before. It seems particularly useful for speedrunning, learning glitches and stuff. But I've never tried making my own scripts. Right, what was... So the trick I used was, okay, so this... Let's use pencil. No, not pencil, that's too small. So we have a grid of items, right? So my idea was, if I want to find the sum of items in this square, say. So we've got a bunch of items in the square. We want to find the sum of all of them. Well, you could just count each item one by one, add them all up. But that's a lot of repeated work if you're then going to do another square later on, which overlaps this one. So what I'm doing is I'm taking 4 different squares, 4 different rectangles. So there's this rectangle, this rectangle, and then this rectangle, and this big outer rectangle. If you already have computed those 4 rectangles before, then you can immediately get the sum of this square by taking the big one. Okay, I need to put some letters here. So let's say A is the big rectangle. B is the rectangle, which is like... Well, I can't even draw this diagram. Hang on. Okay. Get rid of that line. Do I have a bigger... All right. This rectangle here is A. The one that it's contained within. This is B. Basically going around those two. This one is C. So it's like here. And then the big one is D. So if I do D minus B minus C, that's basically taking away this section and taking away this section. So you end up with just this left, but you've subtracted A. You've over subtracted A. So then you add A back in, and then you should just get this grid. Equals, let's call it E. So that's my... If in the past I've already computed A, B, and C, and D, then anytime I want to get E, I just have to do D minus B minus C plus A. That's an optimization. It cuts out about a factor of 300, I think, because then you only need to work with rectangles which start at the top left always, instead of rectangles which start midway. All right. Well, anyway, that's just me reminding myself how that worked. So now this has to be a square. So we can say for x1 in range 300, for y1 in range 300, for, let's say, for D in range max x1, y1. Okay, that cuts out a whole for loop. Then we want the sum of the rectangle from x1 plus D and y1 plus D. Alright, so we want to know the best xy that we've seen so far. We want the best power that we've seen so far. Let's say we start at just minus some big number. If so, P equals that. If P is bigger than what we've seen so far, then we update what we've seen so far. And best xy will be xyd will be x1, y1, and D. And then after this, we just print best xyd. Oh, let's see how fast that runs. Oh dear. I think we had to remove that one there. No, hang on. Let me think this through. If D was 0, let me rename this to size, then I can kind of get a better understanding of this. So let's say the size of this rectangle will range from let's do what I was doing before. So x2 will range from no, size. Let me think this over for a minute. Oh, I see. Starting with 0. Yeah, 0 indexing is used everywhere. Oh yeah, size isn't gonna go up. It's gonna start from 0 and range up to this number. Ah, okay. So it will be, take that out. So it would be range from 0 to, so let's say the square was of size 299. Square started at 298. Well, no, 299. That means there's only room for one tiny little corner in the bottom right. So that means we would want 300 minus the max of those two numbers. So if x1 was 299, then 300 minus 299 will be 1. So we would do range 1. So that would be one element in the bottom right corner. I think that's right. So then we range from x1 to x1 plus size minus 1, and y1 plus size minus 1. Hello, DJ. I did start earlier. Yeah. Yeah, I had more time today, so I started earlier. Probably, if I finish, I mean, I think I'm about to finish this problem. I don't know if I'll have more time after that. Let's see. Then again, it's raining heavily, so I might want to go on a bit longer. Let's try running. Okay, that's a reasonable time frame now. Before it was taking too long. 1,217,62. Okay. We can try that. I'm not sure. 1 is a strange. When is monsoon season for Vietnam? I guess now, but I don't really think of it as monsoon season in Southeast Asia because the rain only really comes in short bursts. I don't think they really have monsoon season here. I know in the Indian subcontinent they have monsoon season where it just rains for days and days without stopping. But everywhere I've been, for instance in Thailand, where I was staying for like over a year during the pandemic, I never experienced any monsoon, and I was living on the tropical islands. It was more just like it would come in short bursts during the day, but it wouldn't really last long. Depends what people mean by the word monsoon, but I think of monsoon as rain which lasts for days on end. But I've not seen that happen. Like in Jumanji. Jumanji is where I learned about monsoons. I don't like the fact that X is 1 here. That just seems suspicious. Alright, so we'll go with... Oh, I need to add 1 to these, so it's going to be 218, 62. Two, 218, 62. I'm not that confident with this. No. Because I feel like there are several places where I could have the index off by 1 and so on. So when they say size, they mean that many elements in the rectangle. Alright, well, we can actually test our theory here by printing what we think the best power is, where it is, and then separately we can just add those up from the rectangle and see if that actually adds up to what we got. Let's try that. So I'm claiming that in this rectangle we get 1860. Okay. So separately I can write a test. We can say for x in range, so it'll be starting from 1 finishing on I think there's some off by 1 errors here. Okay, finishing on, so it'll be 62 plus 1 plus 1. Because we finish on 63. No. (62 plus 1). Yeah, for y in range from 217 up to 62 plus 217. P plus equal power grid yx print p. So if this gives us 1860, then that just raises more questions, because then I don't know what's wrong. Okay, that's not 1860. Something's gone horribly wrong here. These methods are a bit of a mess. Two 2018 seems harder than the other years. I don't think so. I think I remember one year being a bit harder. I think some of the past problems I've overcomplicated a bit, and they were easier than I thought they'd be. This one is not actually that hard. It looks like I've got all the indices wrong, that's the problem. The method is actually one that I've seen. It's actually a popular interview question. Find the rectangle in this grid, the square in this grid, which sums to the highest value. And you could just try every possible square, but that takes too long. So I've tried to use a process to... Let me bring out my paint again. To be able to compute squares based on rectangles you've computed before, without having to recompute them. It's not very obvious from this diagram now, but basically I'm trying to say if I want to find E, which is this square here, then I would have to do D, which is the whole big rectangle, minus B, which is the side rectangle, minus C. But because we've minused the A section twice, we have to add back in A, and then we get to E. So that's the optimization I'm using. But because I'm doing so many additions and subtractions, it's possible I've got indices wrong in some places. Let's start from the bottom and work our way backwards. So let's see if the final method is actually sensible. Best XD. So we range x1 to... So we're trying every possible coordinate of the starting point of the rectangle. For every possible size... Okay, wait a minute. We should be starting from 1. You don't start with size 0. Let me try running that again. Size 0 doesn't make sense. Alright, well that didn't affect anything. Okay, so we range from size 1 rectangle to 300 minus max. That's basically... Let's put in some more values here. So then x2 equals x1 plus size minus 1. So that's the finishing coordinate. And y2 equals x, so is y1 plus size minus 1. Let's say if x2 is greater or equal to 300, or y2 is greater or equal to 300, that means we've gone off the side of the grid, so this doesn't make sense. So skip these values. Alright, so now we don't need that. So we can say p equals get some x1, y1, x2, y2. If it's better than what we have before, update that, update that. Alright, so I think that method is safe. It's just get some is probably not safe. Let's try running it again. $1860, same as before. Okay, fine. So get some is probably flawed somehow. So this is saying the grid which starts on this value and ends including this value, get the sum for that rectangle. And that's basically the Microsoft Paint diagram here. We're taking the big rectangle, subtracting the yeah. Why 1 minus 1? Yes, that's correct. Then we've got x1 minus 1. And then we have to add back in the x1 minus 1, the y1 minus 1. Okay. That looks correct. All these numbers, it's a lot of numbers, yeah. I don't really like the way I've done this. If I were to redo this, I would put all this stuff into this method and make it recursive. I've done an iterative method. Okay, so the tricky bit is when we have rectangles which are like one width and they're like along the side of the grid or something. In those cases, the sum still applies, but some of these sums are null. So if it were one width, then the x1 minus 1, this would go off the side of the map, so that would just be 0. So you would just be using the same rectangle that's one width, but one element shorter. I think that would work. So maybe the problem's here then. What have I done here? For dx in range 300, for dy... Alright, let's change these variable names, because d is confusing. Let's say... Okay, for x in range 300. So we're saying... So yeah, if x and y is 0, that means we're just talking about the very top left grid element, so it'd just be that. That's correct. If y is 0, that means we're talking about a very short rectangle, which is just along the top row. So it would be table x minus 1, same y value, one x value shorter, and then add in the current. If x is 0, then we do the same thing, but other way around. Okay, so then otherwise, the normal case is where neither x nor y is 0. So then we do the rectangle thing again. So it'll be x minus 1 to y, x to y minus 1, x minus 1 to y minus 1. Basically doing the same thing we did here. Get some... Maybe we're better off just... Or get rid of this method, this thing here. Just make this fully recursive so it handles any possible rectangle. That might be cleaner. Yeah. So get some handles any rectangle. Alright, let's comment this out. Table. Fresh table. So we're saying, given any x, y values defining a rectangle, if the bottom right corner is for some reason negative, then we skip this. Okay, so return 0. If okay, so we don't actually need this. Okay, if x2 is 0 and y2 is 0, that means the rectangle is just a one element thing, just the top left of the whole map. So we return power grid 0, 0. Take this one out. Otherwise, if we recognize this, if we've computed it before, then we return what's stored in the table. Otherwise, S equals this whole thing. That's the key equation. So this is recursive now. So it'll go to... It'll take the big rectangle. Minus the left the upper rectangle minus the left rectangle minus the smaller rectangle. And then return S. There's one problem here though. Oh yeah, we haven't handled the case where... Okay, if x1 is 0 and y1 is 0, this is a special rectangle because it starts at the top left. So in that case... we do roughly what we did up here. We do this formula. But it will be... Oh, this is so confusing. So it'll be... y2 minus 1 x2. So we add these two together. So we're adding the upper part, adding the left part. That covers the intersection twice, so we then need to subtract that. And then finally we add in power grid x2 x2. Okay, fine. So if we take all that out now, I don't know whether I trust this method now. That's still horrible. But at least it's in one place. Try running it and see if we get a different number now. It's taking a while. Okay, it's spit out a different set of numbers now. That's good. We were hoping for something different. Two, 3, 7. All right, let's change these numbers. So it's saying if we start from 2, 3, 7 with size 9, 2, 7, 7, size 9. So hang on, that's we. So now if our final test gives the same p-value as what we got there, 88, then we've sort of tested our own answer. Let's try that then. Wait for that to hit 300. I think the key to doing this problem and not getting stuck like I got stuck is really making this more modular. So instead of just piling this all into one big equation, just make lots of little methods, test them individually. 88, 88. Okay, so we've self-tested. I think this will work now. Yeah, the failing really was this method. It's too many indices written by hand. I think the key really is to make this more modular. Make methods which are easier to understand the syntax of, and can test them separately. Basically, what you do when you actually work for a software company. No one writes huge chunky methods like this. That's just asking for bugs. Actually, that's not true. People do write big chunky methods like this all the time, and that's why software is so buggy. And in particular, that's why games are so buggy, because video game design is one place where we do often write big chunky stuff like this. Okay. Because you're under bigger time pressure in game design, and companies are more willing to sacrifice development time in order to get something else out faster. Plus, there's this whole thing now, because now that everything's online, companies know that they can push out a buggy game on release and then just worry about fixing it later, which is kind of scummy, but that's the way it is now. So that's, whereas back in the day, everything had to be on the CD final, because you didn't really want to be providing online patches and stuff, because that was a pain. So you would deliver a final disc, and everything had to be final the day that the disc is delivered. But now, because no one's using discs anymore, you can just keep releasing online patches, which means nothing has to be ready day one. I haven't checked whether this is the final answer though, but I mean, we've self-tested, so hopefully... Right, so we want... Hello, Maro. Every company is implementing the Bethesda model. The community can patch our game for us. Yeah, I mean, that's happening as well. I mean, just a couple of weeks ago, I was playing Vice City. I was using the Definitive Edition patch for that, which is completely fan-made. And it works so well, and it makes the game look so good as well. It's way better than the actual Rockstar Definitive Edition version of that game, which was released after that mod, as I understand it. Alright, so XYZ is 238,278,9. 238,278,9. Ooh, okay. That was not actually, I mean, I got stuck for a while, but I think I still maintain that was not fundamentally a difficult problem. It's just I was cutting corners. Literally cutting corners. But I do like my paint diagram now. I think that does actually help me. Drawing this definitely helped me understand this as well. Because if you try every possible square in the grid, and for each square you count up all the elements, well, let's think about that. How many possible squares could you have? Well, there's 300 by 300 possible locations for the top left corner of the square. And there's times 300, because for every one of those top left corners, there's basically 300 different widths the square could have. So 300 by 300 by 300, that's how many squares we could have. But once we have that, we then have to count up all the elements inside the square. So we have to multiply by another 300 by 300. Because the square, in the worst case, could be as big as 300 by 300. So that's how many things we'd have to add up. So that 300 times 300 times 300 times 300 times 300 is the amount of work you would have to do if you're brute forcing this. So by using this equation, basically I've cut out the final two, these two here. Because even though I still have to try every square, I no longer have to add up everything inside it. I can just piggyback off the work that I've done for previous rectangles. So it becomes 300 cubed instead of 300 to the 5. 300 cubed is in the millions, but it's just enough that I can still do it. It's only a cup trill. Yeah, if it was just one additional factor of 300, I think it would still be doable, but you'd have to leave it running for maybe an hour or so. But yeah, this double factor is just too much. I've definitely seen this problem come up in interviews. I think companies like to ask this problem, but it's not. Yeah, it is actually, as far as interview problems go, I would say this is the harder end, because actually putting it all together, you know, in 20 to 30 minutes on a whiteboard with a couple of like interviewers watching you is pretty difficult. What is this paint monstrosity? I've probably whipped out paint maybe twice before. Yeah, not often, but sometimes I need to whip out paint just to understand what I'm doing here. This is basically saying, if I want to find E, which is that square, if I want to find the size of E, then instead of just adding up all the things in E, I'm taking 4 rectangles that I already know from before. I'm taking D, which is the big one, subtracting B, which is this side one here, then subtracting C, which is this upper one here. But by doing this, we ended up subtracting the A section twice, so we then add in A to compensate for that. It's basically a kind of like a Venn diagram, and then you end up with E. That, yeah, geometrically makes sense. So it's recursion, but a kind of weird way of recursing, because you're kind of recursing on something that could be bigger, but the key is the bottom right hand corner of each of the recursive rectangles is always closer to 0, 0. The bottom right hand corner for E, oh no, that's not true, because D was the whole thing. Well, we're recursing on things that start in the top left hand corner as well. That's also the key. It's a strange recursion. Yeah, I can't think of any faster way of doing that. I think that is the method, pretty much. You had to make that observation. Yeah, I think this is the textbook method. There's probably way cleaner ways of writing it, though. Time for day 12. I think the rain has stopped, and I think it's time for me to head to the gym, because it closes at 8 p.m, which is kind of early for gyms. I'm used to gyms closing at like 11 p.m. or even midnight, but this one closes at 8 p.m, so I gotta get there now. So, yeah, I'll finish there. Gyms close. Well, yeah. Here in Vietnam and Thailand, I think they close because not as many people go to the gyms as they do in London. But when I was in London, the gym would be open 24/7, so you could go in the middle of the night. I think gym culture is less popular here, so they just close earlier. Especially in Thailand, I think the only people using the gyms really were foreigners. Here in Vietnam, it seems to be more commonly used by the Vietnamese. I don't know if that's actually true. It just seemed that way. When I went to gyms in Thailand, it was just always foreigners. All right, well, that was 2 problems, so better than my par rate of 1 problem a day. I'm probably gonna have to set aside several hours to try and get lots of problems done in one day. All right. We're almost at the halfway point. Oh, no, wait. 25. Yeah, we're almost at the halfway point. And... yeah. Stats. That was problem 11. It doesn't look particularly... There was definitely a difficulty increase from the previous... Whoa, okay, 80. Oh yeah, problem 10 had a stupidly easy part too. I don't know what that was about. Yeah, there was a difficulty increase from 10 to 11, definitely. You can see the stars are reduced. Alright. Alright, thanks for watching. See you next time.